As we've seen so far in Chapter 3, we are shifting our focus to using the derivative to tell us more specific information about a function. So far, we've seen in Section 3.1 how the sign of the first derivative tells us whether a function is increasing, going up from left to right, or decreasing, going down from left to right. In this section, Section 3.2, we will see how to locate high or low points, otherwise known as extreme values or extrema of a function, by using the first derivative. This is actually one of the most important applications of differential calculus. Finding the largest or smallest value of a function that models a real-life quantity is extremely useful. We will actually spend some time looking at those kinds of applications of this once we get a hang of the procedures in this section. This section is divided into two separate but related concepts. In the first part, we will discuss relative extrema, which occur on an open interval, and in the second part, we will discuss absolute extrema, which occur on a closed interval. First, let's define what a relative extreme value is. When we use the word extrema or extreme values, that's just a word that we can use to talk about maximum and minimum values. These are the points that are the highest or the lowest, or they're at extremes. The relative part of relative extrema means that we are looking on kind of a small little range of values, or in a little local neighborhood where the extreme value, the maximum or the minimum, is only a maximum or minimum, maybe, relative to points that are really close to it. So it might not be the highest or lowest point over the entire function throughout its whole life, but relative to the x values really close to that maximum or minimum, it is the highest or lowest point. So here is the proper definition of what a relative extreme value is. So we'll be talking about a function f of x, and we have to have the function be defined at the x value of c if we're going to have a maximum or minimum there. So we can't have a hole or a vertical asymptote or a jump of any kind at a point where we have a maximum or minimum value. And that's all that this is saying. So we can have two kinds of extrema. We would say f of c, the y value that we get when we plug x equals c into the function, is a relative or local maximum of the function f if there exists an interval from a to b that contains the x value of c, such that all of the f of x values or all of the y values on that interval are less than or equal to what we get when we plug in x equals c, or the y value at x equals c. So that is a mouthful. It's a kind of complicated way of really just saying, if we look over at our graph on the right-hand side here, that you can kind of point out where we have a maximum value, right? It's right about here, right? This is a high point. Okay, so we would say this is a relative or local maximum. And that x equals c, right, that's telling us where this is located. So we'll call this c. So here is that c talking about in the relative or local maximum definition. Now the f of c, that's the height, right? We kind of will often want to know what is the actual maximum value. Well, that's what you get when you plug in the x equals c into the function. You find how high does this go? And if you notice, like if we just look, so this a to b here, right, that's just the interval saying, okay, like around x equals c, kind of really close. I'm just going to say here's a and here's b. If we look on the graph, then this is actually the highest point around this little area. So that's what we mean by, again, a relative maximum. Because if we look out on the graph over here, it does continue to go up forever. It's what this arrow means. And there are actually y values that are larger. All of these up here and on forever are actually larger than this value here. So this is okay. This is still a relative maximum because, again, the relative part just means in this little area, this is the highest point here. Okay, we similarly define a relative or local minimum value. Okay, we say that f of c is a relative or local minimum now if there exists some interval from a to b that contains your x equals c value, where all of the y values on that little interval are now above the value when you plug in x equals c. So in other words, if we look at our graph, I think it's a little easier to understand what's happening. So here is obviously a local minimum. Now this one's blue, so I'm just going to use the same x equals c value. Okay, so that's the location of that. And if we just look around that point here, this is the smallest value locally or relative to points near it. And again, in the definition, here's what we're just calling A and B in this little interval. This is the smallest value. Okay, and then the f of c, again, that's just the height. So again, we'll want to know what is the lowest value or what is the height there. And so that would be that f of c. And again, this is not the lowest point over the entire function because here we've got even lower y values than what we get when we plug x equals c in, but relative to points near this x value, it is the lowest point. And that's what we're talking about when we use the word relative to talk about extrema. So it is honestly not too important that you have this kind of way of describing relative or local max or min values with the mathematical notation. The graphical interpretation, you should be able to point out maximum and minimum values using a graph. And as we'll see, use calculus to locate these maximum and minimum values. Although these definitions should make sense to you, that a maximum is a point that is bigger than all of the y values around it, and a minimum is a point that is smaller than all of the y values around it. So now let's shift to talking about how to locate these values, how to find these maximum and minimum values using calculus, not by graphing the function and estimating by using a graph. One of really two important pieces that we have to understand when we are trying to locate maximum and minimum values is that they must occur at critical numbers. Relative maximum and minimum values must 100% of the time occur at a critical number. So let's review what that means. What is a critical number? So this is from section 3.1 when we were talking about increasing and decreasing. So what a critical number of a function means is that the derivative is equal to 0 or the derivative is undefined. The critical numbers are the x values. So the way that I've written it, x equals c, would be a critical number of the function f of x if the derivative is 0 or undefined there. Now, why is this the case? Well, if we have a function that maybe looks something like this, then we can clearly point out that we have a relative minimum here and we have a relative maximum here. And at these 2 points, we see that the derivative is equal to 0 there, right? We have a horizontal tangent line at both the relative minimum and the relative maximum. We are going to need to talk about how we decide if a critical number gives us a maximum like this or a minimum like this. We'll need a little more information than just knowing that the derivative is 0 or the tangent line's horizontal there. But here's also an example of what a graph might look like if we have an undefined derivative at a critical point. So here we clearly have a maximum at this pointy place, a relative maximum here. And here we have a relative minimum at this other pointy place. These could be, they're sort of cusps, but we might call them sharp turns because cusps have to come in sort of vertically. So I don't know, maybe this one's a cusp and then this one's more of a sharp turn. But these are points where, if you remember, the function is not differentiable. There's actually no tangent line there. We don't, there's a difference between coming from the left and coming from the right. The slopes are disagreeing at this point, so we can't find an actual slope. But there's still a maximum and a minimum here. So this is what it would look like when the derivative is undefined. at these points versus where the derivative is equal to 0, which is what the left side looks like. So we really do need to check for both of these places, both types of critical numbers, if we're trying to locate relative maximum or relative minimum values. We also need to keep in mind that not every critical number will give us a relative maximum or minimum value. Again, we will talk about how to decide whether we have a max or min algebraically, not just graphically. But graphically, what this would look like is if we have a critical number, meaning that the derivative is 0 or undefined there, but we don't have a maximum or a minimum, that might look something like this, where the tangent line is horizontal and then the function doesn't have a max or min, so it continues maybe to decrease or maybe increase. So here we have a critical number at this point, right? The derivative is equal to 0 here, but this is neither a max or a min. So just because we have a place where the tangent line is horizontal or the derivative is 0, that doesn't always mean that we will have a max or min value. Okay, we could also have the other situation where, maybe the function's increasing and then it's horizontal at a point for a second and then it continues to increase. It doesn't kind of turn around. Algebraically, again, we would still get this as a place where the derivative is equal to 0 because the tangent line is horizontal there. But again, this has no maximum or no minimum. So remember, our goal is to try to identify all of these maximum and minimum values algebraically using calculus, not just looking at a graph. So based on what we just talked about, the difference between having a minimum or a maximum and not having a minimum or a maximum is really on whether the function turns around, whether it switches from decreasing to increasing, or maybe increasing to decreasing. Right here we have a minimum and a maximum, but over on the right-hand side, the function decreases and then continues to decrease. Right? The derivative does not change sign. On this last graph, we have a function that increases and then continues to increase. The derivative, again, does not change sign when we don't have a maximum or a minimum. So this idea is summarized in what is called the first derivative test for classifying relative extrema. And it all has to do with what the sign of the derivative is doing from the left of a critical number and from the right of a critical number.